All right, we are in problem 21. A dinghy is pulled towards a dock by a rope from the bow through a ring in the dock 6 feet above the bow as shown in the figure. Rope is hauled in at the rate of 2 feet per second. A, how fast is the boat approaching the dock when 10 feet of rope are out? At what rate is the angle theta changing at that moment? And I better refer to the book real quick, sorry about that. What is the angle theta that they're talking about? They're talking about the angle between the rope and the dock here. So that angle theta is this angle right in here. And as the boat is approaching the dock, hopefully you're looking at it thinking that angle is getting smaller. Okay, let's see what we've got here in our picture and see what we're working with. Okay, we've got this rope, and we note in the problem, if I draw kind of a triangle here, the rope is through the bow, and it goes through a ring on the dock, and the ring is 6 feet above the bow. So what they're talking about here is this vertical distance going up and down the ring is 6 feet above the bow. So as you pull the boat in, it will always be 6 feet above the bow. The ring, which is up here, and the bow will always be 6 feet. Whatever, the distance between them will always be 6 feet. Okay, maybe we want to label some things here. Again, you're noticing here it looks like a triangle. And so maybe here I'll label going horizontally. I'll label that X. Vertically, I will not label as a variable because that is a constant 6. So I keep the 6. And my diagonal, that's the rope. I'm pulling in the rope. That's definitely changing. And I don't remember in the problem if they labeled anything. So I'm just going to call that distance S. That's the rope. R may have been a better choice. Okay, so the rope is hauled in at a rate of 2 feet per second. At a rate is a derivative, 2 feet. This is the rope. So I know ds dt is 2, and since it's being hauled in, I know that's a negative 2 because S is getting smaller. Okay, part A. How fast is the rate is a boat approaching the dock? So for part A, how fast they want to rate the boat approaching the dock, that's right over here. So the question is dx dt, that's what we're looking for. So what does dx dt equal? When 10 feet of rope are out. So when rope, which was S, when S equals 10. Okay, we need an equation that really relates S and X. And it's the same one we've had, I don't know how many problems now. It's the Pythagorean theorem. So I'm going to write x squared. I'm going to sub in the 6 because, again, it does not change in the problem. X squared plus 6 squared equals s squared. I will take the derivative with respect to time. I do that on both sides. So the derivative with respect to time. On the left side, I get 2x dx dt. Seen that before, haven't we? The 6 goes away. That was a constant. Right side, I get 2. I get s. And I get ds dt. Let's see. Do we have everything? Well, I've got 2. I don't have x. But I know s is 10. I know the vertical distance is 6. So y is 6. I know the Pythagorean theorem. X squared plus y squared equals the hypotenuse squared, or I guess in this case we got that s, don't we? So equals s squared. So I've got x squared plus 6 squared equals 10 squared. I note that's a 3, 4, 5. So I know x equals 8. You can work through that on your own if that doesn't make sense. So I've got my 2. I just figured out x is 8. dx dt is the question. And the right side over here, I have 2. There was 10 feet of rope out. And ds dt was a negative 2. Right side, I've got a negative. Looks like a 40. I'll divide by 16, because this is my 2 times 8. So my final answer is dx dt equals negative 2.5. And my units are feet per second. Let me just make that decimal a little more prominent. So negative 2.5 feet per second. Now, in terms of your intuition, that might seem like a slight paradox. It's not. This is true. But I was pulling in the rope at 2 feet per second. And pulling in the rope at 2 feet per second it makes the boat go at 2.5 feet per second, which is kind of interesting. But when you consider that this rope is covering a larger distance, the hypotenuse is larger than that side, so it's interesting how that works. Pulling the rope at 2 feet per second, the boat comes at 2.5 feet per second. All right, let's do part B. Part B, they want the angle at that moment. So we'll split this up just a little bit. We've got at least a problem in mind. Let's see, one more step here. Got the problem in mind. So what rate is the angle changing at that moment? Let's just keep our picture here. Let's get part B. They want the angle. Again, an angle, you're thinking of a trig function. How about sine? How about cosine? How about tangent? So you go through those possibilities. Would you like the sine? Would you like the cosine? Would you like the tangent? Personally, I prefer the one that uses this vertical distance because that's a constant. I'd prefer the one that uses the rope length because that was given to me. And what if in part A I made a mistake in calculating the x dt? I didn't. I checked it in the back of the book. But what if I did? Then in part B, I'll be getting the second mistake because I'm using my mistake from part A. So I would prefer to use the rope distance and the vertical. Now look at my angle theta, and those two are involved with the cosine. So the cosine of theta is the adjacent. That's 6. That's a constant. It doesn't change the problem. I can sub that in right away over the hypotenuse. And it looks like I've outsmarted myself a little bit because that's still going to be a messy derivative. Let's take the derivative with respect to time. Take the derivative with respect to time. And the left side, the cosine, that derivative is negative sine of theta. And I get my d theta dt. The right side, I have 6 over s, otherwise known as 6s to the negative 1. So the derivative is negative 6 over s squared, because that'd be s to the negative 2. And then don't forget the chain rule, ds dt. Okay, we're almost there. I wish I knew the sine of theta. And again, we think of that triangle we have here. Here's our theta. This was the 6. The rope was the 10. We previously calculated x. We know in this problem x was 8. And so I know the sine of theta, SOHCAHTOA. Sine is the opposite over the hypotenuse. It's 8/10, which I know also reduces to 4/5. So let's sub in. I've got a negative. Sine of theta is 4/5. d theta dt is what I'm looking for. And on the right side, I've got a negative 6. S is 10, so 10 squared is 100. ds dt, they told me at the beginning of the problem, was a negative 2. And I'm looking at all these negatives, getting a little bit worried. But luckily, there's 3, so my final answer will be negative. Because I know from this problem, as the boat's being pulled in, clearly that angle is going to get smaller. So I'm expecting a negative answer. Let's solve this for d theta dt. Let's see, it looks like a 12 over 100 from the right side. Looks like I'll divide this by a 4/5 or multiply by the reciprocal. There's a negative on that as well. So multiply by negative 5/4. 4 goes into 12/3. 5 goes into 120. So my final answer, d theta dt, is negative 3/20. And the units for an angle are radians per second. The angle part is radians, and in the problem they mentioned that it was seconds. This completes our dinghy problem.